when you start digging around and you get into investing, you will notice this doubling effect for compound interest very often is captured by this rule of 72. So I just want to point out, where does this rule come from? Now, it doesn't actually originate in terms of the derivation, as I will point it out in this video, because it has been used actually before even calculus was discovered. So it's been probably around 1500 or 1600 when I was starting to look it up. Okay, kind of the first instances popped up. Now, I'm sure maybe you would even find it even earlier. Now, this particular rule is pretty simple, and it's extremely useful because you can do a lot of mental math very quickly, trying to see how quickly your money is doubling. So the rule simply says, so here in terms of n, so n is just how many years it would take to double your money. It is just equal to approximately 72 divided by the interest that your money is compounding in. And that's a very easy and simple formula. And you can, of course, rearrange this formula, and you can find out in terms of the interest. So what interest would you need if you wanted that particular money to double at certain points? Okay, so let's say in 10 years I want to double my money, or in 20 years I want to double my money. Then you can rearrange this, okay, and you can solve for your interest I. Now, in this case, interest I is in terms of percent. And kind of the general case, which I'm going to just show you right now and introduce it to you. So within here, so this is the doubling shortcut. Now, you don't need to actually understand compounding the formula itself, although if you've landed in here and you want to know exactly where did it come from, then you can certainly kind of fast forward a little bit and you'll see, okay, that it just comes from the Taylor series, or kind of the McLaren series, if you like, from calculus, and I'll show that in a moment. But before I get into that, I just wanted to give those folks who wanted to be able to see how to use this rule of 72. Okay, so on the left-hand side, it is an estimation rule, so it's not exact, but boy, is it pretty damn good, especially for, interest that we're kind of interested in. So let's say, I don't know, between 1 and 25 or even 50%. Okay, so it's relatively good in terms of its approximation. And so what it does is, so here's some common examples on the right-hand side. 72 as a number is a really nice number because a lot of the smaller numbers will go into it. Obviously, 1 goes into it. So, if your money's compounding at 1%, then it's going to take you approximately 72 years to try to double your money. So meaning going from $1 to $2, or from $10 to $20, or from $500,000 to $1 million, because that's the doubling effect. Now, if you are compounding at 2%, then it's going to take you 36. So that's 72 divided by 2, and that's 36 years. Now, take a look at 4%, so 18 years. So again, you can just simply plug it in and do that math relatively quickly. Or 6%, or 8%, 9%, 12%. So all of these go into 72 very, very nicely. And actually, when I end this video, I'll point out that 72 was pretty much chosen for that reason, because it's not exactly 72 in the approximation, but 72 just has so many kind of numbers that nicely divide into it. Now, of course, this doesn't mean that you can't use, 3% or 5% or 10%. You can do that, and you can clearly, very quickly try to approximate. So for example, you can take 72 divided by 10, and then it's approximately 7 years. So it would take approximately 7 years to double your money if you were compounding at 10%. And that's why, when you are investing, and if you're starting to think in terms of doubling effect, how quickly can things double? You can very quickly figure that out. So for instance, if you are investing and on average, you're getting about 10%, which is kind of almost very close to historical over the last century, that would mean that you would be doubling your money in approximately 7 years, maybe a little bit more, but let's round it to 7 years. So, let's say if you started, with $10,000, you would double it to $20,000. And then again, if you continued that, so the next double, so from 20, it would go to 40,000, and then from 40,000 to 80,000, and to 160,000, and 320,000. So you can see that these doubling effects, if once you get to a certain amount, they start to matter a lot. So in fact, let's say if you get yourself to 100,000, well, then doubling means that you're going to get to 200,000. Let's say if it was within 7 years. I normally don't really shoot for 10%. I mean, that's kind of a gift. I'm not that ambitious. Okay, but I do try between 7 to 10%, although I've been lucky. I've done a lot better than that. Okay, but that's just been honestly just luck because I am very passive in terms of investing. I'm starting to be a lot more active now. Now, this rule is you can just kind of keep it handy. The opposite you can certainly do as well, because you can say, well, what if I wanted to double, my money, let's say in 10 years? So you can use that rule. So you can rearrange the formula. You can say, all right, so 72 divided by 10 years is going to give you approximately 7%. So what that is telling you is, you should try to invest in such a way that you are going to be compounding at 7% annually, and that will take about 10 years to double. So you can do that both in terms of finding out how long it takes you to double, or if you already know how fast you want to double, then you can find out what the interest rates would be, and then you can kind of research and then set it up either passively or become an active investor. So that's kind of the first thing. That's the shortcut itself. So that is just gives you an idea of how that works. Now, in terms of the true compounding formula, so I'm going to kind of scroll it back in here, and then we're going to get into the derivation. So the true compounding formula is this formula right here. Now, if you really want to find out about this particular formula and even kind of where it comes from, I'm going to put up a link. I used to make and I used to teach actually mathematics for business, and compound interest was one of the nice things and nice features there. So it's a really cool thing to learn. But I would say that almost everybody should learn at school at some point, although they don't really teach it. Okay, that rule of 72 in terms of doubling, and once you get into investing, you start thinking about money, it's super useful. Now, by the way, it's not just money, it's compounding anything. You can have population growth, you can have virus which spreads, right? So anything that kind of starts to grow exponentially, okay, on a compounding basis, you can use this formula for, and you can very quickly find out, how quickly things double. And you don't really need a calculator for it. You might sometimes need a little piece of paper or something just to do some kind of math, or even you can do it some mental math. But once you get used to it, okay, enough times, you very quickly pick it up. Now, the main formula is this for compounding. Now, what it says is, I'm not going to necessarily go into as much detail. You can watch the link that I provided. But what it states is, if you're starting with a present value in here, this is going to be the future value of your money. And the compounding formula, notice it has n in the exponent. Now, within here, n means the number of periods, okay, that you are actually investing for. And then I is actually the interest itself, and we're dividing by 100 because here I just assumed that it was a percentage. And sometimes the 100 is not given there because they just assume that you're plugging in a decimal. So now if you are assuming that it is a percentage, then you can have that. And in order to solve for the doubling impact, the true formula is actually right below it. So if you take a look, I'm going to kind of steal this out of here and then just make it really big, okay, so that you can see it. So I'll just put it right above in here, okay. So if you take this, that is the true formula. Now what I am doing in here is I've set the present value. Notice that there's no number in here, although I guess there is because it's a 1. So it's like we're starting with $1 and then we're going to get into $2, which really means just a double, right? It doesn't matter, how much money you have. If you have $10, you want to see it double to 20, you can certainly do that. But then, of course, 20 divided by 10 is again going to give you 2, right? If you take $1 million and you want to double it to 2 million, well, again, 2 million divided by 1 million is equal to 2. So this formula never changes for doubling. But that's not what we want. We want to be able to solve for this n, and it is an exponent, of course. Now, if you want it, okay, so this is where this whole 72 comes from, because you're going to rearrange this. Now, in order to rearrange this and solve for n, you do need a little bit of math. So what's going to happen is you're going to have to take the ln, okay, of the left-hand side, or the log of the left-hand side. That's how we solve for exponents, okay, and then you're going to take the log of the right-hand side, and I apologize, I'm going to use ln, okay, which is the natural logarithm. Doesn't matter which one you use, ln or log, okay, so it will be the same. And then here you're going to just get 1 plus I over 100. And then the rules, okay, so for logarithms, okay, so if you do have an exponent, okay, up on top, it actually comes out to the front in here, so it starts to multiply. And now that multiplication, of course, you know, we can take this, we can divide the right-hand side and the left-hand side by it, and then you're going to get this formula right there. So notice this is exactly where it appears, okay, in the denominator, and you have solved for n. Now you will say, well, that's not 72 over I, and you are correct. It is not 72 over I. And this is the key important thing. Who the heck wants to work out, you know, logarithms or lns, okay, in their head when they're trying to find out doubling? So this is going to give you the accurate, okay, to whatever decimal place you want, how long it would take. Right, so in terms of the doubling impact, we're going to be assuming that we're compounding annually, which means per year. So how many years it would take. But nobody's going to be doing this, and that's not a mental math thing. So, you know, there's a lot brighter people than I am, and they've came along and they replaced this bloody thing with 72 over I instead. So what they said is like, well, you know what, I don't want to use this, okay, so because this is kind of complicated, so can I approximate it with a tool that's very practical? And indeed, there is a tool that's very practical, and it is 72 over I. Now, if you really want to know why they came up with 72 out of here, mathematically, you do need a little bit more math, okay? And so I'm going to just show you where that comes from, so for those who are interested. So if you take this, you can derive this whole thing. I'm going to kind of zoom in here. And it turns out that for relatively small values of I over 100, which indeed we are dealing with small values because, I mean, unless you're going to get into interest rates that are like 200, 300, 400%, right, in terms of, then trust me, if you can get those kind of returns as an investor, okay, you don't need the rule of 72. You know, you're basically doubling so quickly, okay, that you're going to become, you know, basically take all the money in the world super fast. But what we normally deal with is, you know, percentages kind of between 2%, you know, maybe 20%. I mean, if somebody's kind of compounding at 20%, you know, maybe only Warren Buffett has done that in terms of a huge amount of time. Okay, so that's difficult. But those are small, right? Even if you take 20%, you divide it by 100, it's 0.2. So it's a rather small value. So what we can do is, and we can use the Taylor series or the Maclaurin series, really, okay? And we can use kind of the derivations and approximations, okay, for this crazy function over here. Because if we take the real function, ln of 2, okay, or the logarithm or the natural logarithm of 2, that's just a number. We can compute exactly what that number is. In fact, I can tell you, because I'm prepping for this video, so I remember it off the top of my head. I don't always will remember it, but it's 0.69, okay, 3. That's what ln of 2 is. It's just a number. Now it has other decimal places. We don't need too many for approximations. So this we know. We don't need to approximate this at all. This is just an actual constant. It's a number. But this, in the denominator, we want to see how did we come up and that it has become I, right? Okay, because we're dividing by I over all. So it turns out that there is this Taylor series or Maclaurin series that we have. Now I put a footnote in here for myself. So this is what it is, all right? So that's the approximation, okay, which utilizes basically a power series. Now, this is where math comes in. Now, you know, some of you maybe have started to do math, right, in terms of probably in grade 11, maybe, okay, the power series started to come up, okay, it depends. Again, you know, I have done videos on those as well, okay. You can certainly go on into 1mjourney.com and you can go into probably grade 11 and you'll find it. Now, you're not going to find the Taylor series itself because that's later on in calculus and you need the derivatives. And what it states is you can take this and approximate it as closely as you want it to, okay, by using this power series. And then what smart people do is, okay, if x is very small, right, in this particular case, so now for us, x is I, divided by 100, right? So it is going to be small. So if it's like 0.2 for 20%, for an example, well, if you square that, 0.2 squared is 0.04. So this term becomes almost negligible. And this one, because you're cubing it, it's even smaller and smaller. So what happens is we ignore all of these terms, right? We approximate it, and it becomes just a linear approximation, okay, with respect to this crazy function. And it's just simply x. Now, in our case, for x, what we have is, notice, x is just I over 100. Hence, we're taking this thing out of here, and we are approximating it by I over 100. And if you now substitute it back into here, this is what you're going to get. Now, that 100, because it's in the denominator, fractions, it will go up into the numerator. And then ln of 2, as I said to you, it's 0.693. Okay, it's, there's some other decimal places. And if you multiply it by 100, you're going to get 69.3 divided by I. And there you have it, right? So that is your rule. Now, you might say, well, it's not 72. Well, you're bloody right. Who the heck wants to use 69.3? Right? So what they've decided, now they could have rounded it to 70, and they could have made it a rule of 70. Now, my guess is, and again, just kind of by looking around and researching, they didn't pick 70 because 70 doesn't have as many divisors, okay? Kind of like, 2 and 3 and 4 and 6 and 8 and 9 and 12, etc. All of these go so nicely, okay, into 72. So they kind of picked 72. The other component is, because of the 72, it actually approximates it really, really well in a very good range. And I'll show you, because I'll pull up decimals and I'll show you the true value versus the 72 divided by I value. And it's going to shock you how close they actually are. So those two particular functions for n. So the 72 is just much easier to use than 69.3 or even 70 for that matter. So that is kind of where it has started to go. And honestly, it's been a long time, probably about 500 years, again, in terms of finance, much earlier than, this whole calculus stuff has come around, okay, which came afterwards. So they were poking around and they figured out this rule a little bit faster. But this, okay, now just kind of gives you and justifies why indeed it is true. So they just approximated the 69, they kind of rounded it up to 72 because they wanted a lot of these interest rates, okay, to go into it much faster, and it's easier to do mental math. That's where it has come from. So now that you know where it has come from, you can certainly research more about the Taylor series if you really want to know, okay, or you can just simply use it, right? You can just say, all right, let's try to use it, and now you have a big trick. Warren Buffett uses it. All of these guys constantly use it. They're not using logarithms. All right. If you needed calculus to do well in investing, Warren Buffett said this, then it wouldn't have worked for him. Right. You just need kind of simple math. Now I want to just show you how close the true value is to 72 over I. All right, so here it is. So I prepared it so you can see there on the left hand side. So it says 72 over I. And so that's kind of right here. That's what I'm doing. And then there's the real formula, ln of 2 divided by ln of 1 plus I over 100. Now I'm doing it between 1 and 50. So basically what I'm saying, compounding at 1%, all the way up to 50%. And then I'm just increasing it by 1. So 2%, 3%, etc. And now I've mapped them out. So what you see, so the true value, okay, I'm going to just show you. This is the true values. And what it does is on the x-axis, that's your I, your interest. So it starts off at 1%, okay? So the true value, okay, of in here, if you were compounding, it's actually approximately 70 years. The rule of 72 would have given us 72 years. So we're off by a couple of years. So it's not terrible, right? But we also don't really want to compound at 1%, so we wouldn't even catch up to inflation. Now, if you take to 2, okay, so what that is right there, so it tells you it's about 35 years, right? Now, notice 2%, if you use the rule of 72, well, 72 divided by 2 is going to be 36 years. So that's pretty damn close. We're off just by a year. But now what happens is if you go to 3, okay, and 4% and 5% and 6%, now they get really, really close. So instead of just showing you the numbers, I want to graph both of them. So again, keep in mind the red dots that you see, that's the real. So that's the amount of time that it would take for the real one. And then the interest rates keep going. And notice that it just kind of has this nice real curve. It is, from compounding in here. But notice that even at 3, so if I go in here, okay, so you have a 3. So 3 goes into 72, okay, so we have 24. And the real one is 23.449, whatever, okay, within there. So that's now super close. We're off really by half a year. Now, if you now keep going in here, if you take the next one, okay, I'm going to try to see if I can even, because they're so close, maybe I'll just do this. Okay, so I'll just show you. So this is for 4%. I don't know if I can even click this. All right, there you go. So at 4%, 18 years, right, by the rule of 72, and 17.67, so 17.7, basically 18 years. That's how close they are. And notice that they just get closer and closer and closer. And this is like pretty remarkable because it's so damn good in terms of an approximation. Okay, notice all the way up to, I'm going here, 15%, 16%, 17. They're just so close. 20%, 21. They're still, now they're starting to spread out a little bit more, but it's so close in between them, right? Like even if I take 31, okay, notice this, okay, they're very, very close together. So the error does get bigger, but again, if you're starting to compound over 20%, like honestly, it just so quickly doubles that you're not going to be worrying, okay, about the rule of 72. However, okay, this now just shows you, how beautifully aligned they are. Now, I'm going to actually show you that, like even if you were doing it as a continuous function, like this is how basically they just line up on top of each other. So this rule of 72 is remarkably good. Now you know where it has come from, you know how to do it, okay, in terms of its derivation, and then the reasoning why they picked 72, again, is because just so many numbers, okay, go into 72, much easier, okay, than the other ones. And we don't want to be using the real formula of compounding because nobody's going to be doing logs in their head. So there you have it. Okay, thanks for watching. I hope that you found this useful. Okay, take care, everybody. Okay, hopefully you hit a like and you subscribe. Welcome to the 1 million journey. Okay, I hope that you watch the episodes. Cheers, everybody. Bye.